Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on the 25th of June, 2025 T 9 hours 40 minutes and 50 seconds, 0.0000Z. This paper, published just a few days ago, introduces a model that gets superior results using less than 0.01% of the training data of other methods. The paper is titled, From Ideal to Real, Unified and Data-Efficient Dense Prediction for Real-World Scenarios. And this ability to work with so little data is really what makes it so interesting. The authors tackled dense prediction, which is basically teaching an AI to label every single pixel in an image for tasks like segmentation or depth estimation. Also, the authors shared their implementation on GitHub, and it's quite comprehensive. You'll find the full source code to train and run inference with their DenseDiT model. They also provide the pre-trained model checkpoints for all 25 tasks in their new DenseWorld benchmark, which is a great resource for anyone interested. On their Hugging Face page, you can find the DenseDiT model. It features great visual examples for dense prediction tasks like depth estimation, fire alerts, and crack detection. So, to really set the stage, the authors provide this great visual comparison. On the left, you see what they call idealized scenarios, things like clear outdoor depth estimation and simple indoor object segmentation. These are well-lit, clean images where current models perform quite well. But on the right, we see the real-world scenarios, like depth estimation in fog, crack detection on a road, or even identifying oil spills. These images are noisy, complex, and highlight exactly the kind of challenging, data-scarce problems the authors are tackling with their new approach. So to address these challenges systematically, the authors created a new benchmark, which is basically a standardized test for AI models. This figure gives us an overview of their benchmark, called the DenseWorld benchmark. You can see on the right, it covers 25 different tasks, everything from fog depth estimation and medical imaging to smart city analysis. What's really key here is that each task has only 15 training samples. This design forces any model to learn very efficiently, which is the whole point of this research. Building on that benchmark, this next figure shows the architecture of their model, called DenseDiT. The core idea is to reuse a large, pre-trained generative model, a diffusion transformer, or DIT, which is kept mostly frozen to preserve its powerful knowledge. To adapt it to new tasks, the model uses a variational autoencoder, or VAE, to process the images. Then, two lightweight branches enhance its understanding. A prompt branch uses text to explain the task, while a demo branch can show an example. Crucially, they use LoRa modules for training, which means only a tiny fraction of the model is modified, making it incredibly data efficient. Moving to the results, this table really drives home the point. It compares DenseDiT against other general-purpose models on that new benchmark. And the most striking column is training samples. While other models use thousands, or even over 1 billion samples, DenseDiT uses just 15. And yet, if you look at the performance, measured by a unified D-score and S-score, where higher is better, DenseDiT consistently comes out on top across all categories. Its final average scores are significantly higher, proving this new architecture is not only incredibly data efficient, but also much more effective. And the numbers are one thing, but this figure gives us a fantastic visual comparison of how well DenseDiT performs on these tricky classification tasks. We see 4 examples here, from finding a single cigarette in a pile of debris, to identifying fire, to outlining spinal structures in an MRI. In each case, you can see how other models like SAM or ClipSeg struggle. They either miss the target or produce noisy, incomplete masks. But DenseDiT's output is consistently clean and remarkably close to the ground truth, which is the correct answer shown on the far right. Beyond just classification, this next set of images shows how DenseDiT handles pixel-level regression tasks, which, in this case, means predicting a continuous value, like distance, for every single pixel. We're looking at depth estimation in really tough conditions, fog, sunset, rain, and overcast weather. And you can see that while other models produce blurry or incomplete depth maps, DenseDiT captures fine details like distant lampposts and creates much sharper, more coherent boundaries. This ability to understand the whole scene, even with limited visibility, is really what sets it apart. So, what this all really demonstrates is a powerful new approach for a very practical problem. The authors tackled the challenge of dense prediction, which are these pixel-by-pixel tasks like segmentation and depth estimation in messy, real-world scenarios where good data is scarce. By creating both the challenging DenseWorld benchmark and the incredibly efficient DenseDiT model, they've shown that you can achieve fantastic generalization, meaning the model works well on new, unseen data using just a handful of examples. It's a significant step for deploying AI in the wild. That's all for this edition of the AI Research Roundup. Thanks for tuning in.